So it's a pleasure to continue this event this afternoon with Mohammed Abouzaid from Stanford University. Mohammed, thank you for coming, and the floor is yours.
Thank you very much. So, as some people know, I've been spending a lot of time in the last few years, and probably in the next few years, thinking about Floer homotopy theory, which is some attempt to bring in methods from homotopy theory to the study of quantum flirting and the more general constructions of exactly topology. And that was the initial idea. And now, we've been doing this with Blumberg for a few years, and we realized that the way to actually do things is in some sense to go the other way. If you take the constructions which naturally are derived in geometry and flirting with Morse theory, and try to reinterpret the constructions of stable homotopy theory from that point of view. And that, in some sense, it's a continuation of a very long history. And today I want to talk not about Floer theory per se, but about some small part of this project that can be stated without all the machinery of Chai categories, elliptic medians and so on. So the starting point, the main result that I want to state is here. So what's the point? The point is that if you take the category of topological spaces, let's take the base topological spaces at the base point. So the base point acts like a zero, like you have a zero. But at the beginning, you don't have addition. And you can ask yourself, what's one way of creating addition from the structure of this category? And this was answered a long time ago. And what you do is you observe that the circle has a coproduct. There's a natural map that draws here to Stanford Blackboard from this circle to itself, which makes this with this. Okay. And that means in particular that if you have two maps out of the circle from this X and this another X, you can draw that. Another map, that's here. That in G. Then you can just define the sum to be this composition. This composition of this projection map with these two methods. So that starts to make it like your category. Once you have this circle in the source, it starts to make it like your category not only has a zero, which is the base point, started with also an addition. If you do this twice, this operation is actually does not have a problem together. That's what you do if you plus that. But if you do it twice, and if you also work only up to homotopy, then you will now have something unitive operation. Okay, and so now this is the building block of what is called the stable homotopy category. Instead of looking at these topological spaces, we're going to look at topological spaces where we allow ourselves to add and multiply our spaces with S1. Technically, we don't really multiply it to modify base point called extension. Okay. And there's a theorem that says that if you look at the category of topological spaces together with the notion of homotopy, then there is a category which is uniquely determined as a universal property, conveying its ability. Okay. And that's what's called stable homotopy. And so when people do operator studies, more model theory, it's the place where universal additive invariant topological spaces. So what I want to talk about today is a statement that there is a model for this category, which unlike the other ones, if you have these more, it's not built out of combinatorics, it's not built out of this kind of homotopy theory, it's built out of bordism and Morse theory. And of course, to indicate what I mean by Morse theory is more like the spirit of Morse theory. It's not going to, you don't need to talk about manifold functions on them. They're the kind of data that comes out of Morse theory. If you combine it with bordism, you get some interesting model for the stable. And I just want to make clear, this is not useful for computation. Okay? This is not meant for you to be able to compute, the 200 second homotopy group of an object. It's not what it's for. It is meant for constructing structures, to kind of, get some situation where kind of build some complicated algebraic structure. This allows you to do it geometrically, where sometimes it's much more difficult to do so. Right? And so the nature of this talk is going to be that there is some kind of oscillating wave of difficulty, because there's kind of three subjects going on here: homotopy theory, Morse theory, and bordism theory. And so hopefully it's something that can make sense on this slide, and on the next slide something else will make sense. Okay, so what is Morse theory? I'm going to assume no familiarity with the subject. So Morse theory is the idea developed by Morse, where he managed to tie together dynamics and topology. Okay? So dynamics here, in this case, meant the study of geodesics on spheres. And he proved this wonderful result that was inaccessible that we ever need at the time, which is that if you take a sphere with an arbitrary metric, arbitrary dimension, arbitrary metric, and you take 2 points, then there's in fact infinitely many geodesics in that. I'll remind you that the geodesic is a critical point of this functional, but really what you should think of it as, if you look at paths, most paths have a property that you can perform a little bit and change their area to first order, but geodesic are those which are critical. So when we draw things, when we kind of, ones we think about when we are living in the space that we live in, tend to be minimizers. Straight line. This is a minimizer. If the only perturbation you can do to it makes it longer. But already on the sphere S2, if you take the great circle, this is clearly not a minimizer. It's a critical point, but if you perturb it a little bit, things will become shorter because you can keep pushing. And what Morse managed to show is that this phenomenon persists. It persists even if you change the round metric, in which we can describe everything explicitly, to an arbitrary metric. And how did we do so? He said, well, take these 2 points, P and Q, the right 2 over there. Okay. And for a second, just don't think about geodesics. Think about all paths between P and Q. This is a topological space. We can study it. And we can study in particular its homology. And we showed that its homology is non-trivial at infinitely many degrees. And those infinitely many degrees, he then worked out, basically correspond to the infinitely many ways you can go around a great circle when the 2 points agree. So you can go once, twice, 3 times, so on, so on. Every single one of those. The subject of Morse theory tells you that every single one of those corresponds to a generator of a homology of the space of paths from P to Q. Okay? And moreover, a generator in a different. And because it's a generator in a different degree, they cannot cancel once you start to disform it. So you could have imagined that this thing that goes around once and the thing that goes around twice, if you do some perturbation at some point, they kind of come together and disappear into thin air. But that cannot happen because we managed to prove that they have homologically eccentric functions. Okay. So there's one ingredient in this work of Morse that's a little bit technical. And it's about studying how you make this connection, which you have to study this function on an infinite dimensional space, which is the space of all paths. And functions on infinite dimensional space can be very complicated. Where the essential point that makes the machine work is that there's only if you have a critical point. This is what this second order definition of the critical point is to do that. Then the space of ways of disforming it, and making it smaller is finite dimension. And so that means that even though the whole space is infinite dimensional, the contribution area of which is finite dimensional, that's why it's a cycle in ordinary motion. So Morse's method for proving this is a little bit crude, because what he did is he said, really the argument goes like start with things which have 0 energy, well, negative energy, there are none, then go to energy to the smallest level of energy, that will be the minimized geodesic, and then inductively analyze the topology of the space as you work up, as you work your way up the energy filtration. And at each step, you show that the change in the homology is exactly accounted for by the creation of the visits, and so therefore there has to be complementary, because eventually there has to be a. But it's a bit cumbersome because you have to do this step by step. So the next evolutionary theory, there are many of them, but kind of qualitatively for me is using Whitson. So Whitson said, you don't have to do it. You don't have to do this analysis where you go step by step. You can just take the whole thing at once. So what does that mean? That means, so I'm going to go down and simplify my life without doing infinite dimensions, because it's a version for this dimension. It means if you take a metric, and it has a Riemann metric, and the choice of more function on it, second technique works now, there's like a generic here, they want to give intelligence or that. Then you can construct a chain complex from this data. And this chain complex computes the homologies, the cohomologies. Now, Whitson did this with Riemann homology. These days, you know how to do it with ordinary, you have to put on the Z coefficients. But it's proven to do it. So how do we do this? Well, this complex, as I said earlier, is going to be generated by critical points. So here's a critical point P, here's a critical point P. Okay? This is a maximum, this is a saddle point. And the chain complex is not just a collection of generators, it's a collection of, you also have differential. But if the chain complex is presented as generated by a set, the differential is a matrix. Okay? For each element P, I have to tell me what is the coefficient of Q in the differential. That's this based on matrix. And now the matrix is going to count something. What is it going to count? Well, with it said, it's going to count gradient flow lines of the function f. So that means solution to the equation, sorry, I'll write it again, b gamma by dt equals minus gradient of f. That will be gamma of t. Solutions to the 3D, something we'll teach, undergraduates, except they don't usually do use the target manifold, but it's not a big deal. Solution to the 3D, on what domain? On the domain which is the real line, to your target manifold, which I did there's a map from here to here, let's solve this equation. And now I said with asymptotic conditions, which go to P and Q. So let me just write the limit as t goes to minus infinity of gamma of t equals. You have always a convention, but here I'm going to make it Q, and the limit as t goes to plus infinity of gamma of t. This is what you're supposed to count. One proviso is that if you look at this equation, you see that, you can translate gamma by some amount and you still have a solution. So you have to look at the modularized basis, which is being mod out by the R action. So you count the state, okay? And that's the coefficient of the matrix. You call that matrix V. Okay? And then you check that somehow but the V1 with respect to some natural way of counting, actually, just with respect to the Morse index, which in this case is 2, in this case is 1. And then you have to prove these verticals here. And this is the tricky point. This is the thing that really kind of is contributed to the story, which is that this proof that these verticals 0. Well, if I go from P to Q and the index changes by 1, and go from Q to R and the index changes by 1, then from P to R the index changes by 2. So to prove this vertical 0, I have to say something about flow line, gradient flow lines, just like I said here. Gradient flow lines between things, the critical points P and Q, index difference is 2. And what happens is you can show that this space of a solution is now a one-dimensional manifold, compact one-dimensional manifold with boundary. And there's a kind of the first basic statement that students learn in topology is that a closed one-dimensional manifold with boundary has an even number of boundary points. And if you orient it, you can count the orientation to count the boundary points with appropriate signs, and that the number is 0. And that turns out to be the proof that we see here. It's a extremely geometric proof. You extract something algebraic from the data of the geometry. I'm happy to take any questions from trying to get the background. How do you use it? So this is an ODE here. So what you can do is you can but it's somehow a little bit degenerate because of what's happening at infinity. Okay? So there was an ODE finite time, and of course there is a moving substitution. But here at infinity, what you find out is that the space of solutions, the dimension of the space of solutions, should be related to the difference between the dimensions of the descending manifolds, which are nothing. And then there's a -1 because of the argumentation. Yeah, exactly. Geometric manifolds would have to be two-dimensional, but it has an arc translation, so you're that's a very good question. Okay, so this is Morse theory, Witten, and this is basically the starting point of Floer theory. And now Floer has this paper. He doesn't have that many papers, but he has, they're all brilliant contributions to the literature. Right, so this one is about Witten's Morse complex. And this is this remark that I put here, as you can tell, the paper starts on page 207. It's 14 pages long. Halfway through the paper, there is this remark. Okay, and it says something like this. I'm gonna just say words, both if you want. It says when we define the Morse complex, and let's include the principal coefficients, we have to count with signs. So we have to make sure that the moduli spaces are oriented. But when we do Morse theory, in fact, the moduli spaces are more than oriented. They are stably framed, like it's framed. And if they are framed, that means that there is possibly more structure, including more structure in higher dimension, or higher dimensional moduli. So that remark is completely correct. Okay. So then he says, we should therefore be able to do the following thing. Instead of computing ordinary models, we should be able to do generalized homology theories. For example, for general, let each of us do generalized homology. And, he said, well, we can try to do this by J complex. Now, unfortunately, you cannot do it by J complex. Okay? It's a long, back in the 60s, it was proved that the only cohomology theory that can be functionally computed by a chain complex is ordinary cohomology. Okay? Nothing else. Everything else requires more sophisticated theory. It could be by accident you can do a chain complex, but morally you shouldn't be able to do it. But if you already, he said this, and then again he said, there should be a spectral sequence. Okay, that's actually the way. If you want something very at the level of groups, and don't want to say something more sophisticated than that, that is what you should go for. You should go for a spectral sequence that converges to the cohomology of the space, starting with some kind of more theoretic thing. Okay. But the first slide I put up said there is a model for the stable pattern, something much stronger than saying there's some spectrum. So that's I want to kind of keep building up until we can see how to get around this issue. Okay, so I want to say a few words about fluency motivation, even though this will not show up again, but I think it's kind of important to know what he was trying to do. So he was trying to think about, again, some kind of Morse theory in infinite dimensions. But his setting is not that of a Riemann manifold, his setting is that of a symplectic manifold. It's a symplectic manifold M and symplectic for omega. And he takes a diffeomorphism with the property which preserves the symplectic form. We call this symplectic morphism. Roll back to omega. Omega is a 2 close to. Okay, and he is interested in the fixed point. The fixed point of this. And there's a full floor computation that has been known. I mean, well, he was doing this in the 80s, it was known in the late 60s for sure. Okay, and it says that these critical points, these fixed points that we're interested in, you can interpret them as critical points of some function. some function that is defined where, well, on some loop space, but more precisely, the loop space has to account for this p. So it's not called sort of twisted loop space. The twisted loop space, actually, I do it here for the loop. So the twisted loop is basically you give yourself the data of a different morphism of your space, or if you want just any mapping space itself, if it's a different morphism is good enough for us. And then you look at paths which go from which end at a point here, and then start at this stage. So they make a loop if you allow yourself to close that line. So on this space, on the space of such paths, you go gamma 0, they're not fixed, we can move around as long as they are related by the speed. You can write a function. Actually, the function requires some choice, the choice of primitive. So you take the symplectic form, okay, and you write it as D-lab, as the differential of the one form, and then you can just integrate the one form along the path. That's all. It gives you essentially path number. And then this function, the smooth function of the space of twisted paths, you can look at its critical points and you realize that its critical points are exactly when this path is zero, exactly when gamma 0 equals gamma 1. That's it. So you want to do the same thing. You say, I'm not going to do Morse here. There's some trouble. So its first trouble is that, when I described what Morse did, I said, if you look at the geodesic, you try to see how many ways are there, second order, of decreasing its length. You always see a finite dimension. But that's not the case here. What you get is something like controlled by Fourier modes. Negative Fourier modes will make things smaller, positive Fourier modes will make things bigger. But there's always infinitely many Fourier modes. So it's not a finite dimensional path. And then the other problem is some technical problem about compactness of the it makes life even worse. I'll allude to it at the very end, what it has to do with the Anyway, Morse succeeded. And he proved that if the symplectic form is exact, which means that then there's this primitive that you need to write out the action functional. That's what it means, the primitive action to find globally, rather than just locally. Then you can do everything with Morse theory, you get this waiting con. So that's the basics of something. Now, how did we do it? So as I said, there's some problem. There's a technical problem having to do with negative gradient flow lines. And he basically said, look, this is a P, okay? When we look at it in the critical point, when we look at it in finite dimensions, there's finitely many ways of going down. And there is this another critical point, finitely many ways of going down. And the space of gradient flow lines between them is some kind of difference. The difference between this two-dimensional space of going down and one-dimensional space of going down from R, and that's one dimension, so that's why there is one gradient flow, a discrete number. Okay. But it didn't matter that these were finite dimensional, there were finitely many ways of going down. The only thing that mattered is that the difference was finite dimensional. So if you imagine that this is like a peak of a mountain, and this is the saddle point, we're going hiking, you could be someplace where there's infinitely many ways of going down. That's the setting of the action function. As long as there was infinitely many ways of going down were basically matched up by the gradient flow line with the infinitely many ways of going down from R up to some finite ambiguity, you would be okay in the rest of the. And that's exactly what we're doing. Okay, so there's this exactness assumption. It turns out that the exactness assumption is not just a technical condition, it's real. It's not just a condition that you can simplify, it's essential. And if you drop it, you cannot define well-defined flow complex. You cannot obtain well-defined flow complex in this by the same method. But Takaya Ono and Liu Tian produced something over Q. And the reason they produce something over Q has to do with the fact that in that case, you don't encounter manifolds anymore. You encounter more general logic. Okay? And today we would call them derived or, but again, let's not get into technicalities, we'll come back to this. I said there will be some peaks and drops of complexity. Hopefully this is a peak of complexity. Okay, so now we've switched to something completely different. So this was the story for homology. Okay? And Floer already suggested that possibly we should be able to do more generalized homology than these. And the one that I'm interested in is stable homology. The stable homology has an essential role in the theory because it's the initial theory. So I don't want to call it the simplest one, but it's the one that is most topologically constructed from the data. So, what could we study? First thing we could study about it, these are base spaces. If you have this one thing, well, as I said, that corresponds to zero. Zero. So you could have one base point and then one other point. That is called less than zeros. SZ. And we said that what we're interested in is not spaces, but spaces up to suspension. And if you suspend a zero, you get a one. And if you suspend a one, you get a two. We were going to put in n spheres for all. And the natural invariant that people study is, it's kind of first one that people would study is this space of mass between spheres and spheres in the stable range. So I probably should have written something that's a limit there. So I should have written something like this. The limit as k goes to infinity of the space of homotopy classes of mass would be written like this, S n plus k to S. Okay. And the point is, this k is varying, and this n is fixed. And this is called the nth stable homotopy. So the unstable homotopy group is some kind of central question. What are these groups? We do not know. I mean, we do not know. As a community of mathematicians, we do not know. People who spend their lives computing them have gotten pretty far. They can go as far as n equals 90. But it's not just that they've gotten very far by sitting down and kind of applying the same method over and over again. They've gotten very far by developing ever more elaborate theories, which every decade or so produces the next example. So it's really kind of a very good subject called theory. But a long time ago, in the 1950s, Pontryagin and then later Thom realized that there is a completely geometric description of these spaces. It doesn't use so much word. The word homotopy uses the theory of bordism. So if you have a map from SK plus N to SK, one thing we learned when we teach our students is that you can approximate every map between manifolds and this map by smooth map. So you can assume that this map is smooth, that costs 2 times. And we also teach them that if you take a smooth map, you can assume that it's transferred to any given submanifold of the target. So you can assume that this map from SK plus N to SK is transverse to, let's say, 0. And then you take the inverse image. If you look at the inverse image, what do you have? As n plus n, yes, n. Here you have 0. And here, let's call this that. Now, and you have another element. If this is transverse, then this is a submanifold. But we don't want to think of it as a submanifold because later we're going to let k go to infinity, so it doesn't matter. And not only that, but there's a little bit left. If you try to describe the tangent space of this manifold, you realize that it is the difference between the tangent space of this and the tangent space of this. And okay, they're not exactly trivial, but they're close enough to be trivial. If you remove one point at infinity, these two tangent spaces are trivial. And so you get this notion of a frame, stably framed manifold. So that's what this is. Manifold n. So that if you take together with the data of an isomorphism between the direct sum of the tangent space with a real vector space of rank A, and a real vector space of rank K plus n. And this little n basically is exactly the dimension of this big N. So up to adding a piece, up to adding a trivial piece, the tangent space. So I use the word bordism. So if you haven't seen this before, it just means that instead of studying the set of such spaces, you put an equivalence relation. And the equivalence relation is that if you have two things, like this, and there is a space of one higher dimension, then you say that n0 and n1 are equivalent. And of course, in this case, because I have this condition of attention spaces, I have to assume that the W that I put in there also is stable, compatibly with the stable framings on the side. So that's the theory of bordism. And this theory is famous because Pontryagin tried to use it to compute stable homotopy groups and made a mistake in dimension 4. So this is part of the reason why the entire development of stable homotopy theory was done on what I call the Thom side. The Thom realized that, Pontryagin is trying to use coordinates to compute stable homotopy, and Thom does actually the other way. He wants to compute homotopy theory using mortals. Yes, yeah, so yeah, exactly. Yeah, one right now. Okay, so this is the Pontryagin. And when I say that the result, the main result that I want to talk about is some statement that says that you can build a model for stable homotopy theory that is built from manifolds and bordism. This is what it's general. Okay, so how would you do this? Well, so there is this suggestion of Floer that we should be able to extract generalized cohomological invariants from Morse theory. Okay. And this was formalized by Cohen, Jones, and Siegel in 1993, 1994. The paper appeared in the Floer Memorial Volume after Floer passed away. And they have this notion, which in some sense encapsulates what is the abstract output of Morse theory. The abstract output of Morse theory is a category. There's a category whose objects are the critical points of the Morse function. So before I had, and I'm not going to be able to draw, there's pictures on the board. So I had this function here, there was a P, and there was a Q here, and so on. So this is a critical point, this is another critical point, and simplistic picture, what you would say is, my category has two objects. So you would abstract this as. And what are the morphisms? The morphisms are spaces. In fact, they are manifolds. So instead of a morphism being the set, I really want a morphism to have this extra data. It's a smooth manifold with coordinates. Exactly. Which smooth manifold with coordinates? In the concrete situation, the smooth manifold coordinates consisting of all gradient flow lines that go from P to Q. In the abstract case, you just say some smooth manifold coordinates. But it has some properties. So I'm sorry to actually write everything. So first of all, I should have assumed that it's proper. But the fundamental thing is that if you have a manifold with corners, then it has some codimension one stuff. Okay, the way you think about it is there is a boundary, and the boundary is broken up into pieces. So the boundary is broken up into pieces, and each piece of the boundary is identified with some composition. The product of morphisms from P to Q and Q to R for some intermediate critical point when you're doing concrete theory. In the general case, just for some other. The way this is set up is because I assume compactness, it turns out that there's no morphism from something to itself. This is automatically a category which is the objects are partially ordered by the notion that they're being morphism. Sorry, what? No, I didn't. Non-unital. Non-unital category. Yeah, if you make it unital, like it becomes more. So just that's the way it is. Non-unital. Okay. So what I'm trying to say is that this is an output of Morse theory. If you, there's also some output of Floer theory, as long as we are in some generic situation and life is not too complicated. And Cohen, Jones, Siegel showed that if you give me this data, there's one more relationship that they're saving rate, the more than the if you give me the data, then you can extract stable homotopy pattern, which means you can extract space. But the space is not canonically defined. The space is defined up to extension. So how do you do this? You just run Pontryagin-Thom in reverse. So I will only illustrate the first case. So if I only have an M and Q, okay, only two objects, and one space of morphism between them, and if I go up to these notions up there, what I see is that this is actually a closed manifold. And it is frame. Stable. And the fact that it is stably framed tells me that I can produce a function from a sphere to a sphere so that it appears, so that this manifold MPQ appears as F inverse of Q. And if I have a map from a sphere to a sphere, then there is a standard construction in algebraic topology which takes the coordinates. And the only thing that it does is it says, well, when you take SK and you take the union with the disk of dimension n plus k plus 1 along the map which takes the boundary of the disk, which is Sn plus k to S. The picture that one would normally draw is something like this, and then some complicated sphere mapping into it by some map. Glue them together, you get a state. For example, if you just do something as basic as S1 and S1 go into itself by multiplication by 2, you will get R2 out of this construction rather than this. Okay, so this is the Cohen-Jones-Siegel construction, the first case of it. And what they do is they always start with this, okay? And in the next step, what we will do is we'll take another sphere and we will attach it to this again by some map that is constructed either using Pontryagin-Thom, inverting Pontryagin-Thom, and producing some homotopy. So the issue, so this construction is correct, mathematically correct, almost really spits out the right answer. But it is extremely cumbersome. It produces a space. If you try to study the space, it has been presented to you with this canonical filtration. Everything has been rigidified. If you want to consider maps between these spaces, it's essentially impossible because you have to undo the construction. But if you want a geometric interpretation of what is the homotopy within the space, no idea. Yeah, what? Yeah, it's actually, so yeah, the homology of this thing will come. It is not connected. So I actually wrote it in such a way that I made things a little bit ambiguous. It turns out that as I wrote it, I actually have given you a space, I've given you a space up. Most of the time, people study this in a setting where there are only finitely many objects. So then sometimes they'll just suspend so that everything is possibly zero. Your case is possible. No, my case has everything. Yes, there's a, yeah. And that's exactly solid. Okay, so this is the starting point. So let's think a little bit about this. Yeah. What can we do beyond this? So now comes maybe the place where it's easy to get confused. Okay, I just talked about some notion called a frame flow category. Okay? And now what I want to do is I want to make a category whose objects are these things. Okay? Now this makes some sense. There's I just said Cohen-Jones-Siegel showed that if you create a frame flow category, you can obtain a stable homotopy, which basically means you can obtain space. Just ignore them. So spaces have maps between them. So similarly, frame flow categories should have maps between them. What are they? And the surprising thing is, and again, there's almost nobody doing Floer theory in this audience, so they would not be surprised. But I'm going to say that the people who think about Floer theory have actually known about these maps for a long time. It's just that it wasn't clear that it was formalism that we should study independently of our geometric applications. So the formalism is called the frame flow model. We call it the frame flow model. There is a hint of it in that almost a complete definition in the work of Kaya on coordination spaces, but they're trying to prove that some way of extracting the chain complex from some flow category is invariant under geometric operation, and they give some definition that's very close to this. So what is this notion? So probably the best way for me to describe it is to give an example. Okay? So this picture here is supposed to be some solutions to some equation, but not a gradient flow equation like I had it. Okay? It's something a little bit more complicated. The blue thing is the gradient flow of some function called f1. And the red thing is the gradient flow of some function called F2. And now, what I want to do is on the real line, this same real line here, instead of writing this equation here, what I want to do is I want to take this line, and on the left, I will take minus gradient F1. And on the right, I will take minus gradient F2. And in the middle, I will just interpolate between them. So I will write some vectors. Whatever, if you pick it, doesn't matter. To be honest, it doesn't have to be continuous sequence, but let's just assume some interpolation between these two vectors. Makes it psychologically easier to think when you do this. And you can say, okay, what is the space? What was the space of solutions to this ODE, which at this state, this point converge to, sorry, that was called R2. And what this other point converge to P2, to P1. What does the space look like? Everything that I said, everything that we say in Morse theory about, oh, the space of solution to this ODE, the manifold holds for it. Nothing wrong with it. It's again a manifold in boundary. It's just that its boundary is interesting. Roughly speaking, the only thing that can happen to an ODE satisfy uniqueness of solution. Okay, given initial conditions. So nothing bad can happen in the middle. The only thing that can happen is over here something can happen. Or over here something can happen. But over here, everything is blue. You only see the gradient flow line of F1. Gradient flow F1. Here everything is red. You only see the gradient flow F2. And that turns into this picture. This is a one parameter family of solutions to that ODE, which converge to P1 and up2. And in the boundary, they can break. They can break in two ways. They can break as the gradient flow line of the first one, followed by a solution to this interesting ODE, or a gradient solution to this, interesting ODE, followed by gradient solution to it. That's the only thing that can happen. If you take this structure and you abstract it, you get this notion of flow line. A flow, so M1 and M2 are categories. Now, if you're an algebraist, you know, as soon as I write binomial, you know exactly what these equations are. They just follow from being a binomial. The thing that you need to realize is now I'm going to say binomial, and what it means is I have some manifold with corners. That's how I'm going to flow to, and the corner strata are going to be labeled by the equation that you would impose when you say the word binomial. There's two types of boundary strata. One corresponding to what's happening on the left, the other corresponding to what's happening on the right. What I mentioned one. And again, there's some framing and everything, so we can have to frame it to actually write down the full equations of the compatibility. The frame is to take this entire board, not to suggest that it's complicated, it's just somehow. There seems to be no very convenient way to do it. You just have to like concept that. But if you know what you're doing, geometry tells you what you're doing, it's not. Okay, so now the suggestion is, I told you we're trying to build some model for the stable homotopy category. I told you my candidates for the set of objects for what should be developed in the space. Now I'm telling you what I have developed. But the stable homotopy category is the word homotopy, which means it's very unlikely that somehow the morphisms are really exactly these things. There's partially an equivalent relation. Oh yes, it's a binomial. So if you know the division is associated with the function of different persons, right? Just like the previous one has an associativity. Right. Yeah, I said this in category. There's an associativity function here. No, it's very simple for space. It's actually exactly what it is for text.
So the sensitivity is on the norm.
Yeah, everything's on the nose. Yeah. Here, everything's on the nose. Yeah, absolutely. There's no, we don't use homotopy here. Homotopy is produced by converted. Oops, sorry, okay. So now, yeah, so it's not enough to know what the notion of bimodal is. You have to know what it means to have a homotopy. Bimodal, it's not really a homotopy. Bimodal is really a bordism. And it's what you would guess. So you look at the first equation up there, and it says, oh, I have B and B prime. And what does it mean for them to be borded? Well, it means that there is some thing of one higher dimension, like I disclosed here. Okay. His boundary is, these two pieces, left and right. Okay, but now you see the pieces on the left and right, those don't have boundary because that was the previous slide. Ah, I'm going the wrong way. This was the previous one. So this one already has this boundary. This one already has this boundary. So we cannot expect that the first line becomes for everything we want. But well, there should be more boundaries. Sometimes they're exactly like the ones that B and B prime have, and these maps are compatible with the ones that B and B prime have, and they're associated as well. This is a bordism. Again, I don't want to overstate this point, but if you do Floer's theory, which everybody in this audience does, this is very natural. And another way to say this is, I think you put some vector field interpolating between this and this. Now imagine that you don't have one vector field, but one parameter family of vector field. One parameter this way, but also another parameter this. So there would be a P associated with what's happening here, a P prime to what's happening here. You think about what is the boundary of that moduli space. Well, you could go to the end of the moduli space, which is P, other end, P prime, or they could be breaking into two ends. That's never going to disappear. It's always going to be possible. So that accounts for all these. Once you formulate this notion, you can say, oh, now I'm going to look at bordism classes. So finally, I can have something close to a definition for you. So the category that is going to model the stable homotopy category spaces, which is the category of spaces up to maps are given up to suspension, and things are equal if they are homotopy after sufficiently many suspensions. Ignoring technicalities having to do with infinities, infinite dimensional spaces, which I don't want to get into right now. But anyway, that category is modeled by, is the claim mentioned is equivalent to the category of brain flow category, flow categories equivalent to these modules, which are bimodules up to bordism. So let's do a special case. The special case is what we call the unit category. Okay? So Dima pointed out correctly that I said flow category is different like units. In fact, it turns out that if the flow category has one object only, then in this formalism, there are no morphisms whatsoever. There's nowhere for them to go. There's just no more. The structure is very simple in that case. If you look for a bimodule, let me go back a step. If you go for a bimodule from the point category to itself, you see these ends, they don't exist. This unit category, they don't exist. So there is no boundary line. So flow as a set, flow star star, this is flow's medicine. Now, I've been, because of the level of detail, I haven't been saying things like, oh, you can break it up by dimension, let's not worry about that, that's flow's medicine. But in the next slide, I said, oh, modulo by which they border possible. So we can model by this relation. But as I said, these two lines here, they don't exist at all when you're looking at the unit category because there's no more to be on. The only thing that exists is topic. So that topic is exactly what I was saying. So in this very complicated structure that Floer saw, that Cohen-Jones-Siegel formalized, okay, you look at the simplest Morse function, which is a Morse function, one critical point, only nothing else. What you see is the bordism theory of a point, which is the subject of Pontryagin-Thom.
Frame.
Frame, if you put it frame, yes. You have to make a decision. Here I said that closed mental state, frame, closed mental. Frame, closed. But you see, that is a choice. The fact that we decided to do stable frame, we came from the very beginning when we said we do frame flow categories. Very beginning, I said Let's go back 2 steps. It's going the wrong way again. Really matter this. I said a frame, so and with morphisms are stably framed manifold with corners. I can replace this with anything I want. I can replace this with stably complex. I can replace it with spin C. I can replace this with quaternionic, whatever you want. It doesn't matter. It doesn't matter. But of course, if you do that, then in the next step, you better replace this with the correct adjective. Stably. Okay? So that it's just a short structure that you make at the beginning. Of course, if you read the classical textbooks on bordism theory, there's the book of Song, the great book of Song, which is bordism lecture notes. Bordism, which has like a chapter, maybe chapter 4, with like 22 different bordism theories, something. I haven't checked all of them, partly because some of them don't have lack some stability problems, so I don't really anyway. But like 2/3, the ones who ever come, they all fit in. Questions? Okay. So now, so there's just said there's this unit category which corresponds to the point. Okay, and it's useful to kind of think about specifically what happens when you take morphisms from it. Low, star, M. Okay, so more I can have the bimodules, so something has 2 inputs. But why don't we fix this one? And look only at this. So this is what we would call a right M module. Okay? There's also a left M module if you want. If you ask me about the duality between left M module and right M module, I would tell you standing away at duality. That's what it is. But anyway, let's just stick to one. Okay? And now I claim that there is a theorem that is analogous to Wiggin's theorem, and it says Morse bordism is ordinary bordism. Okay? So what do I mean by Morse bordism? I take a Morse function of a smooth manifold X. Okay? I produce from it this flow category, MF. Okay? Then I feed it through this machine, okay? Which means I think of it as an object of this category, and then I look at the space of map, the set of maps from point category to M, which means I look at the set of right flow modules up to point. And that is now the theorem says that this is the same as the ordinary bordism of F, and of course I should have been precise with the frame everywhere, because that's the setting of the working window. The proof is actually not so hard once you have the right tools in mind. The proof says, there is this, maybe do it here. There is this notion of a descending manifold that you can associate to each critical point. So the descending manifold here is 2-dimensional, the descending manifold here is 1-dimensional. Okay. And now, if I have some other manifold, the thing that we're interested in, the bordism class, and mapping to this target X, then what we can do is we can take transverse fiber products. We can take X, N cross over X with this, unfortunately, terminology is like a W in it, W and stable. And this, if you set it up correctly, and if you take the correct compacification, which takes a little bit more, this is a manifold with corners. But you see, it's a manifold with corners that depends on which critical points you have. So it's one manifold with corners for every critical point. And you can ask yourself, what are the boundary spots? And if you look at the boundary spot, and it's closed. Okay? Look at the boundary spot, and oops, I've been pushing this button. You look at the boundary spot, and you get this. That's just what happens. So what you get is you get a flow bimodule with no M1, there's only M2. You get this solution. Because I assume that everyone is counting by it. Okay, so that's essentially the proof. Well, this gives you a map in one direction. It tells me that if you give me a frame bordism class, then I can associate to it this kind of Morse bordism class. And you have to prove that this is equivalent. And to do that, the best thing is you can do it by hand. It's kind of messy. But there's also a way where you do it by saying, oh, well, things are filtered. This kind of Morse bordism is filtered by the action function. And in fact, ordinary bordism is also filtered by the action, right? Like a truncated value. And so all that to do is understand what happens when you skip, when you pass through a critical point. But a critical point is one object, one thing is happening. And for one thing, we already computed. We already checked it for one point. We had we got for this mobile point. That's what I was discussing earlier when I was talking about this. And this proves it for a point. You have a map of those spaces, the associated gradient are isomorphic. Okay, we're done. Except that when you use this filtration argument, this is actually part of the structure of the category flow categories. And it uses the fact that this category is called triangulated. So we'll elaborate on the details, but in particular, the triangulated gives you that whenever you have this flow by model, so B from M1 to M2, you can construct a cone. The best way to think about this cone is like this. You have some function, you have some manifold M1, it's a function, F1. And let's assume for now that it's the same manifold, M is a function F2. And then you can write this function. You can build a function on, roughly speaking, M cross 0, 1, which has the critical points of F1 that are raised in degree by 1, because this is an X. And the critical points of F2 in degree that you have. That's how you construct it. Now you have to think, well, what is the gradient flow line? What does it look like here? That's for some details. So there's this cone, and the cone fits in this. The cone gives you this logarithmic sequence on. That's how you actually implement this proposed proof that I suggested on the previous slide. And now there's one more fact that you have to prove, which is that with respect to this triangulated structure, you have a generator. And the generator is units, and the statements, you go through a bunch of stuff like a compact generator, these are technicalities, and it tells you that a flow category is equivalent to the trivial one, if and only if the homotopy classes of the map, in our sense, which means the bordism classes of bimodule from the units category to it vanishes. So now, so far, I've tried very hard to use minimal amount of technology. Now, the next step is you just have to develop and swallow the pill and accept to just work in not just in the money triangulated categories, but in some more elaborate world of a stable quasi categories. So, but in principle, if you knew that this triangulated category came from something with more structure, so if you're algebraic, if you knew it came from the PG category, we're not talking about PG category either, or something like that, then this kind of theorem suggests that the entire category is determined by the endomorphisms of one object. And that's what this paragraph says. And this is what we proved. So once you know that you have to have one object, try to compute it. I try to have my units object, I can try to compute it. Now, very classical fact in algebra, very simple fact. If you have a ring, I should have called the ring with a big R, okay? You have an algebra over it, which is free of rank 1, okay? Then it's in fact isomorphic to R. It doesn't have a choice. Basically, there it has a unit, and everything is R times that unit, and it's free. Nothing left. This is a very convenient fact, because it turns out the same thing is true in the world of stable homotopy categories. Okay, so I now allow myself to, this is the last slide, feel confident that I'm allowing us to do whatever we want. So in stable homotopy category, every ring whose underlying spectrum is the sphere spectrum is equivalent to the sphere spectrum. That's it. So that's what we want to, that's how we do it. So it's everything I said so far. I said it in terms of categories and coordinate classes and homotopy classes and so on. In fact, I'm trying to use those words to deal with words that I use. But actually, everything we do, we actually do at some level, space level, which technically is implemented using quantum physics. So when I was saying flow is a category, really I meant flow is some infinity one category. When I said the flow is triangulated, really I meant flow is a stable quantum category, things like that. In that world, you can now apply this principle. And it tells you that to show that this category is equivalent to the stable homotopy category, You just have to compute the endomorphisms of genetic operators. And you don't even have to compute it as a ring by this principle. You just have to compute it as it states. So that's the Pontryagin-Thom theorem that I started with. I started by saying the unstable homotopy groups of spheres are given by this, and by Pontryagin-Thom, you can think of the statement like that. You need a little bit more because it's not enough to get the comparison with other groups. You need a map of spaces that induces the cycle. It's not that. And that's the conclusion. That's the theory. So you take flow categories, you make a category out of them, okay? And that is equivalent as a stable quasi-category to the category. So if you know about the subject, you know that one thing that I've hidden to you about, and I haven't said anything, but what happens when you have infinitely many objects. Very easy. The stable category, part of the stable category is simply finite space is very easy to describe. But in the stable category, there are some objects which have cohomology in between positive and negative. You have to describe them as well. The sphere of absolute velocity, you can model them as well as you want to. That's the okay. So I think at this stage, I may have a few minutes left, or I may be done. I actually have no idea. Oh, I'm over time. So I'll just say, I'll take 30 seconds to say the following thing. So everything I said so far is for bordism. You can do the same thing with other bordism theories. Okay? Now, in reality, this talk was extracted from a series of special cases in the paper that is being written, because the case that we care the most about for applications to Floer theory is not about bordism and many. It is about bordism, some more complicated structure, which now we seem to have converged with column derived results with column combination spaces in the previous situation of the language. Okay, so we have to develop all this thinking. Okay. Next, I've just said something about categories, okay, but now we can do the next thing to say, like, what about constructing gradients in this world? That means there's an algebraic structure on the states. This category is not even going to you can formulate every structure that you would want in that world of flux. And finally, for people who care about symmetry, we know that if you take a Lagrange in the symmetric manifold, you generally do not get a well-behaved, homology group of the product. You get something more complicated called curved A to the R. And it turns out that these formalism actually also can be extended to account. But that will be a few more years before everything. Thank you very much.